In our fourth lecture, I want to take a brief couple of slides to explain the mechanisms that are causing these plates to move. To do that, we'll watch a fun little video. I'm sure some of you might recognize what this is. We have here a lava lamp, and the lava lamp is a great example of the processes of convection. Down here at the base of the lava lamp, you have a lamp. That lamp is heating up the wax, and as the wax heats up, it causes the wax to expand and become less dense. And as it becomes less dense, it rises up in the fluid that is contained. Oh, there it goes. Ooh, yeah, so it's less dense, and so it's more buoyant, and it rises up. Once it gets to the top, it is further away from the lamp, and so it starts to be cold again. And as it gets cold, it gets denser, it's not as buoyant, and then it begins to sink down to the bottom. That's a summary of convection. But what does this have to do with our Earth? Well, convection was the primary idea for how our plates moved. This was the initial hypothesis. This was the old explanation. It is no longer considered complete, but let me tell you a bit about how it worked. Here is a cross section of our Earth. We have the crust here at the top. Here's the mantle, and then we have the liquid outer core. The liquid outer core is releasing heat into the mantle, and that heat causes the material to expand and become more buoyant and rise up through the mantle. And so these locations where the mantle is getting a lot more heat begin to rise up and come up underneath the crust. Once it reaches the crust, it begins to cool down and spread out in all directions. It was thought that this spreading out in all directions was the force that was pulling plates apart. Remember, divergent plate boundaries are the places where the plates are spreading apart. It was thought that this spreading out of the cooler mantle or the cooler asthenosphere would drag the plates apart. This was a pretty simple explanation at the time, and it turns out it's not entirely correct. It does contribute to plate motion, but not like these other two. We do see evidence for the mantle, or sorry, the asthenosphere moving up through the interior of the Earth, but it does not cause enough force to move our plates. What is moving our plates? Well, first up is a process known as ridge push. Ridge push occurs at those divergent plate boundaries where the plates are moving apart from one another. At the divergent plate boundary, there is a force that is pushing the plates upwards. This is all of that magma that is being generated from the asthenosphere at the mid-ocean ridge, at the boundary between the two plates. Because there is an elevation change between the plate and the surrounding areas of the ocean floor, this part of the oceanic plate is actually higher and wants to slide down and move outwards in both directions. And so we call this ridge push because it forms at the ridge and it pushes outwards in both directions based upon the change in elevation and the emergence of new magma that is forming in between the two plates. The second type of mechanism that is driving plate tectonics is called slab pull. Slab pull is a very strong force that is pulling different oceanic plates deeper into the Earth. Remember that the oceanic lithosphere is very dense and very cold relative to the continental plate. this dense slab, this plate, essentially, once it becomes subducted, is essentially sinking down into the earth. And it is attached and connected to the rest of the oceanic plate. So once it starts to subduct and dive into the earth, it pulls all the rest of the plate that is it attached to. And so this is why we're calling the slab, meaning the tectonic plate, it is pulling the rest of the oceanic lithosphere with it. This only occurs at subduction zones, but it is a very, very strong force that is capable of moving the various tectonic plates that exist on our surface.